Good evening and welcome everybody to linear algebra. And we're doing section 1.2 now. As I mentioned, I'm going to go through chapter 1 on the quick side because most of chapter 1 is really things that you've done in high school, just regular high school algebra. But there are some concepts that I want you to see in chapter 1, which we're going to use when we get to when we start to really get cooking, and that's going to happen in chapter 2, of course. So first, I want to introduce you to something which I'm sure you've heard of already, something called a matrix. A matrix, by the way, the plural of matrix is matrices. A matrix is basically a rectangular array of numbers, as you can see right here. Usually you have these two brackets on the left side and the right side, and the matrix, the horizontally, we have rows, and vertically we have columns. So for example, if you look at the in the upper corner, in the upper left corner, it says A11. Now that's not, notice I didn't say A11, I said A11. And if I go to the to the right, it says A12, not A12, but A12. What does that mean? It means that that number, that again, A is just a constant. That number is in the first row, second column. That's why the subscript is 1, 2. So it's kind of like a double subscript. If you go down, if you go back to A11 and go down right beneath it, you see it says A21 because that's the number which is in the second row, first column, 2, 1. Get it? It always goes row, column, row, column. Now we say, if you notice, how many rows are there? There are M like Mary rows. And how many columns are there? There are N like Nancy columns. So we say this is an M by N matrix. We always do, again, it's always rows by columns. So it's an M by N matrix. We'll see some examples of that in a minute, but I just want to talk more generalities here. Notice that I have, again, let's say I start in that first column. So I have A11, A21, A31. So A31 means third row, first column. Those are, it says dot, dot, dot. And then you go down to the bottom, it says AM1, because that's the mth row and still in the first column. By the way, dot, 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 if I had to give a theme for linear algebra, it would be dot, 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 because we always have a lot of dot, dot, dots. So, for example, A sub A23, that number is in the second row, third column, and so on and so forth. And this is an M by N matrix. So if you notice at the bottom, it says each entry Aij. So Aij means the number that's in the ith row and the jth column. Okay, so let's look at some matrices. So here we have a matrix which is just the number. So A is a matrix which just has the number 2 in it, but it's one number, so it's a 1 by 1 matrix. It's 1 row, 1 column. Matrix B is a 2 by 2 because it is 2 rows, 2 columns. Matrix C is you tell me, that's right, it's a 2 by 3 because there's 2 rows, 3 columns. What are the 2 rows? Matrix C. So row 1 is E2 negative 7, and row 2 is pi rad 2 4. Column 1 is E pi, column 2 is 2 rad 2, and column 3 is negative 7 4. Now we have this idea of sometimes we take a system of equations. Look over here, we have a system of linear equations on the left side. X minus 4y plus 3z equals 5. So we have something called we can make an augmented matrix out. We can rewrite this system of equations, get rid of all the plus signs and minus signs and equal signs, and get rid of all the variables, and just write the plain numbers. So if I just have the coefficients, that will be a coefficient matrix, and we see that all the way on the right. If I would have the coefficients but also have the constants, then that will be an augmented matrix. That's what we call it, and it's all the way, and that's what's in the middle. So the constants in this case are 5, negative 3, 6, and that's the fourth column in that middle, in that matrix, in that augmented matrix. Okay, so again, this is just a way of taking the system of linear equations and just rewriting it as a matrix. I haven't done anything fancy. I haven't done anything really. All I've done is just rewrite it in a way simpler way, because now, how do I know what's what? I got rid of all the variables. Well, that's easy, because I always make sure that the whatever the x variables are, I always make sure that that's in the first column. The y variables are always in the second column, and the z variables are always in the third column, and the constants is always in the fourth column. So there's no real confusion there. Notice that in the bottom row, it's the third row, second column, notice there's a 0 there. Now, in the equation, there was no 0, but in a way there is, because really there's nothing. It's just 2x minus 4z equals 6. But it's really 2x plus 0y minus 4z. Or it's also that. And when I write equations, I don't bother writing the 0y, but when I write a matrix, there has to be something in every entry. Every spot has to have something in it. Okay, so now there's something called elementary row operations. If you recall, in section 1.1, we mentioned that when you solve equations, there are certain things you do, and this list that you see in front of you right now is the same as what we talked about in 1.1. You interchange two rows, you multiply a row by a non-zero constant, you add a multiple of a row to another row. This is something we talked about in 1.1. Now, what we're saying is that we could do these same operations to a matrix. We can interchange two rows of matrix. We can multiply a row times a non-zero constant. We can add a multiple of a row to another row, and so on and so forth. And now, what we often do when we do this, we like to make notation. We sort of like to make a running notation of what we've done. What I mean is like this. Look at example A. So in example A, I started with my original matrix, and what I did is I interchanged the first row and the second row on matrix A. And I note that if you look at all the way to the right side, it says notation. Notice it says R1, double arrow R2. That means I interchanged row 1 and row 2. That's how I note that operation. Now, it's always a good idea to keep a running track of what you did when you mess around with the matrix. Let's say I want to take the same matrix, but what I want to do is I want to multiply the first row by 1/2, which will produce a new first row. So I'm not going to do anything. I'm not going to mess around with the second and third rows, only the first row. So here's my original matrix. It's a different matrix. Sorry about that. Here's my original matrix: 2, -4, 6, -2, and so forth. And what happened is that top row now became 1, -2, 3, and -1. But if you notice, all the other rows are the same. The second row is 1, 3, -3, 0 of both matrices, and so forth. Now look at the notation. What I write, the way I note that is I say 1/2 R1 becomes the new R1. So 1/2 of the old R1, the arrow means it becomes now the new R1. So this is the new R1. Now let's say I want to add -2 times the first row and add that to the third row and produce a new third row. So here I'm taking a matrix. Again, these are all different matrices, doesn't matter. And I have to make it type small so it can fit. Okay, so for C, I started my original matrix. And if you notice, the new matrix, which is the first two rows of the new matrix, are exactly the same as the original first two rows. The only row that changed here is the third row. Why? Because I added something. I added -2 times the first row onto the third row. So what happened was that if you look at the third row in the original matrix, the 2 became a 0 because 2 minus 2 times 1 is 0. The 1 became a -3 because 1 minus 2 times 2 is 1 minus 4 is -3. And 5 minus 2 times -4, which is 5 plus 8, is 13. and so on and so forth. And the way I indicate that, the way I note that, is I write R3 plus -2 R1 becomes the new R3. That's how I read that red notation on the right side. R3 plus -2 times R1 becomes the new R3. By the way, if you write R3 minus 2R1 instead of, that's also fine. Okay, moving on. Now, here is, so let's say I want to do elementary row operations to solve a system of equations. Now, this is really nothing new under the sun. I'm just doing what we always did in high school. And I'm just, doing matrices instead of with variables. So I start with this system of linear equations right here, right in front of you, and I rewrite it as a matrix. So I write it like this. So now this is the associated augmented matrix. Oh, there's something I forgot to mention. There's certain words here. Sorry, I forgot that. Notice it says we're row equivalent matrix. In other words, if you take a matrix and do one of these elementary row operations to it, or one or more of these, then the new matrix is called row equivalent. So if I start with the matrix and I do a bunch of these these elementary row operations, then my new matrix is called a row equivalent matrix. Anyway, back to this problem. So now I want to add the first equation to the second equation. So if I do it with a matrix form, R2 plus R1 becomes the new R2. And then I am going to add negative. I'm going to subtract 2 of the first row from the third row. Why am I doing this? Because if you notice, that first row, I wanted to just have a 1 on top, then all zeros underneath it. I have evil reasons why I want that. It's just going to make the equation easier to solve. And then my next step, and then by the way, at this point, I'm not even looking anymore at the equations. You can look at the equations to keep up, but the truth is at this point, I'm just looking at the matrix. But it doesn't matter what you look at. Look at whatever you want. So 1, -2, 3, 9, so forth. Anyway, so where are I up to now? So now I write that, I note that by saying R3 plus R. Oh, so the next thing I want to do on the bottom now, I'm adding the third row to the second row, and that's kind of my new third row. What I've done is that there was a -1 on the bottom row, second column. That -1 now became a 0. That's what I want. I want to get zeros. And now the next thing I do is that I take row 3, multiply it by 1/2, and that becomes my new row 3. The reason I did that is because I wanted to have a 1. I wanted to have what they call a leading 1. Now, this, if you look on the left side, now look at the left side. This corresponds, if I put all the variables back and pull the equal signs back, this is the same thing as saying z equals 2, y plus 3z equals 5, and x minus 2y plus 3z equals 9. And this is extremely easy. It's 3 equations with 3 variables, but it's extremely easy because once I know z equals 2, then I substitute that into the second equation, and that'll give me y equals -1. And once I know z is 2 and y is -1, I substitute those numbers into the top equation, and that'll give me x equals 1. And it's just a much easier way to solve an equation. Now, this is what we call row echelon form, and we're going to see this right now. So a matrix is in row echelon form. A matrix in row echelon form has the following properties. Now, this matrix here, this last matrix here, is in row echelon form. Notice that every row starts with a 1. The first entry in each row is a 1, and I'm sorry, the first non-zero entry in each row is a 1. And also notice that we'll just read it here. A matrix in row echelon form is the following. Number 1, any rows consisting entirely of zeros occur at the bottom. Now, we didn't have that. We didn't see that yet. Or our previous example didn't have that. Number 2, for each row that does not consist entirely of zeros, the first non-zero entry is the 1. It's called the leading 1. And condition 3, which is that if for two successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. And that's why on the top row, that one is all the way on the left. In the bottom row, the leading one is in the second column, and in the third row, the leading one is in the third column. It's kind of that stacked tiered, if you will. Now, that's row echelon form. There's another thing. There's in addition to that, you could do. There's also something called reduced row echelon form. So if you have a matrix that's already in row echelon form, there's one more condition which can make it into a reduced row echelon form, and that's when every column that has a leading zero or leading one will have zeros in every position above and below the leading one. And let's look at some examples here. So matrix A is in row echelon form, but it's not in reduced row echelon form. Matrix B is not in row echelon form at all, because you have all those zeros in the middle row rather than being in the bottom row. Now, for matrix B, if I would switch the second and third rows, then it would be row echelon. It would be row echelon form, although it would not be reduced row echelon form. Matrix C, that's a very beautiful classic case of row echelon form. It's perfect. It's not reduced row echelon form, but it is row echelon form. Matrix D is reduced row echelon form. Yay. Matrix E is neither. It is not row echelon form at all. And matrix F is reduced row echelon. And that's wonderful. Alrighty. Okay. So let's just okay. Now I want to show you something. Here's a system of equation. Here's a system of equation with no solution. And I want to show you how you can recognize that in a when you do a matrix. So I'm going to take these equations here. There are how many equations? 4 equations, and there are 3 variables. It looks like 4 equations, 3 variables. Now, when you have more, okay, it's 4 equations, 3 variables. So I'm gonna rewrite this as the augmented matrix, and I'm going to fiddle around with it. I'm going to, R2 minus R1 becomes 0R2. Or I'm going through this quickly because my point is later on. R3 minus 2R1 becomes 0R3. I'm doing a bunch of steps. Now, at this point, if I get to look at the bottom matrix, so I'm doing a bunch of row operations. And look at the bottom matrix. Look at the third row of the bottom matrix. The third row of this bottom matrix is 0, 0, 0, negative 2. Now, let us not forget that this matrix represents equations. So this would represent the equation 0x plus 0y plus 0z equals negative 2. Well, guess what, folks? That's impossible. And as I mentioned in section 1.1, when you have when the variables disappear, and I'm left with two numbers, and it's false because 0 does not equal negative 2, that means no solutions. But inconsistent is another word for no solutions. And here we see, here the book is showing it to us, of putting the variables back in. Okay, now here's an example. Let's see. Okay, blah 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 blah. Something else I want to show. Let's look at an equation. I want a system with infinitely many solutions. Okay, so here's the equation. So 2x plus 4y minus 3. I'm sorry, 2x plus 4y minus 2z equals 0. 3x plus 5y equals 1. So we're going to write the augmented system, which means we're going to get rid of all the variables and the plus signs, the equal signs, and all that kind of stuff, and just write the constants. Notice that, when I read the equation, I said minus 2z, but really it's just negative 2 times z. So that's why it's a negative 2 in the matrix. Now, what I'm going to do is I'm going to try to put this as best as I can into row echelon form. And what do I get here? And here we go. Now that I get a row echelon form, I even have to reduce row echelon form. The 1052, 0, 1, -3, -1. Now, here we have 3 variables, 2 equations. And there's no problem of consistency or inconsistency, everything's cool. So what I'm going to do, again, that matrix corresponds to this system of equations. And we're going to take, I believe I mentioned this last week, but if not, I'm going to say it now, that if you normally, generally when you have, if you take the number of variables minus the number of equations, that's how that parameter is going to be using. And in this case, it's 3 minus 2, which is 1, so it's just going to be 1 parameter. I'm going to let the parameter represent the x sub 3. And what happens now is that x1 is going to, again, if I plug in t, again, x1 is equal to 2 minus 5t, x2 is equal to -1 plus 3t, and x3 is equal to t, which means and t is any real number, and which means that if I would just now take any number t, I could plug it in and get all these different XYZ triplets. So that's awesome, just like we saw last week. I keep on saying last week, I mean last, whatever, 1.1. Okay. Now, a homogeneous system of differential, if anyone here ever took differential equations, you know that homogeneous differential equations when you have a 0 on the other side of the equal sign. So homogeneous systems of linear equations is the same thing. You have a linear equation, so on the left side of the equal sign, it's just a regular linear equations. On the right side, the constants are all zeros. Now, every linear equation, every homogeneous system of linear equation has at least one solution, because if I let if I let x, y, z, all the different equations, if I let all the variables equal 0, then every equation is true. So every homogeneous system has at least one solution, but let's see if we can find more than just one solution. So here is a homogeneous system of linear equations, and I'm going to put it into the augmented matrix. And now I'm going to see if I could put this into reduced row echelon form, right, or row echelon form. And I do all these steps right here. I'm not going to, you could just follow this, all these steps here. And we now have not just row echelon, but reduced row. By the way, I personally always go and put things into reduced row echelon form, because once you go through the trouble of putting in row echelon, you may as well put it into reduced row. Then it's just much easier to work with. The answers just pop right out much easier. So here I'm going to let z be the parameter, and I get so z is going to be t is parameter t, x is going to be -2t, and y is going to be t. Why is x -2t? Because if you look at that top equation, x1 plus 2z equals 0. That's the same thing saying x1 plus 2t equals 0. Bring the 2t over to the other side. I get x1 equals -2t. That's really how it comes. And this is infinite many solutions, because every time I pick a new t, I get a new triplet of numbers, and all is good. So we see now here a very important theorem, famous theorem, and the number of solutions of a homogeneous system. Every homogeneous system of linear equations is consistent. Consistent is a fancy way of saying it has a solution. And if the system has fewer equations and variables, then it must have infinitely many solutions. Now, that's not necessarily true for a non-homogeneous system, but it's definitely true, always true for a homogeneous system. And you prove it pretty much similar to the proof is pretty much similar to the procedure that we just did in example 9. And that is it. We are done. So let me just let me move out of here, go back here, and we're going to end the chat, and I'll see you guys. Bye.